Okay, so this is the Calculus 3 lecture where we're going to talk about how to do equations of lines. And so in one dimension, it's really the standard plane stuff. We've seen how to do this before. And so what I want to do is I want to talk about how to generalize. So we have, equations of lines. And in calculus, we saw lines are important because, given any curve in calculus, if the curve is differentiable, then locally, you can approximate it very well by a straight line. So we have, what are the different forms of lines we have? Do you remember any of these?
Like the formulas?
Yeah.
So like y equal, like slope intercept.
So the slope intercept. And this is y equals mx plus b. What else is there?
There's I forget what it's called, but it's like y plus a constant. Or like it's like y minus y1.
Yeah, so that's point
slope.
Point slope. Y minus y1 equals mx minus x1. And then there's point, which really what you do is you said m is y2 minus y1 over x2 minus x1. And then once you have that, you then go y minus y1 is x minus x1. So really with point, I like to first find the slope.
Isn't there one where it's like the y plus x equals like some constant or something like that?
No, because it's not always going to be y equals exactly 1x.
No, like y plus x, like on one side equals.
No. So if I'm trying to give you the equation of a line, one way to view the line is, if I have some point on the line, if I move x over 1 unit, how much will the y move up? If I have the line, say y equals mx plus b, how much will y move? It will move up m, right?
Yeah.
So what we can do is we can view this almost as like a slope vector. And I'll let that slope vector v be 1 comma m. So if I change my x by 1 unit, I change my y by m units. What's the one time where this might break down? For what line?
Straight up or
straight up. Right.
Horizontal.
Right. If not, well, if it's horizontal,
actually, that'd be fine.
It would just be m would be 0.
Yeah, straight up. Yeah.
Not vertical. So this leads to multivariable calculus and lines in higher dimensions. So a line has a slope and a point. So what we'll do is imagine I give you some point and I give you a direction. Okay?
Yeah.
Then the line is going to be just flowing through that point in that direction. So let's say the point is x naught, y naught, z naught. Call that point p naught, some initial point in 3 space.
Okay. And
we'll say the slope vector is v, is say vx, vy, vz. Okay? Then the equation of the line is x, y, z, my point, is equal to my starting point, x naught, y naught, z naught, plus t times my slope vector, vx, vy, vz. Or if you want, x, y, z is my initial point, plus t times v. Can you give me a good value of t to try? What's
1 or 0?
0. So if we take t equals 0, that's going to correspond to this point p naught right here. This is t equals 0. T equals 1 would be p naught plus v. Where would t equals 2 be?
P naught plus 2v.
Yeah. So t equals 2 would be p naught plus 2v. And so we can unwind this. If we have, x, y, z, is x naught, y naught, z naught plus t vx, vy, vz, we get the following equations. X is x naught plus t vx, y is y naught plus t vy, and z is z naught plus t vz. So imagine we're just in in the plane. So in the plane, we'd be having xy is x naught, y naught plus t vx, vy. Okay?
Yeah.
Let's see if this reduces to our old equations of the line. So we have x is x naught plus t vx, y is y naught plus t vy. How could I create one equation from this? So I want to get something involving just x's and y's. So what do I have to get rid of?
The x naught, so why not?
Well, the x naughts are fixed. I want just things in terms of the x's and y's and v's. What do I need to get rid of?
Vx, or the t.
The t. How can you get rid of t here? What does t equal? T equals, well, you have this equation. How can I get t from x equals x naught plus t vx?
So x minus x naught over vx.
Over vx, good. And for the second one, we would get
Same
t is y minus y naught over vy. So since they're both equal to t, we get y minus y naught over vy equals x minus x naught over vx. If we cross multiply, y minus y naught is vy over vx, x minus x naught. And if vx equals 1, vy equals m, the slope.
Yeah.
So this is a way to generalize what we've done in the plane to higher dimensions.
Yeah.
And how many dimensions is a line?
2. I mean 1.
It's 1. So for line, once I specify, the initial point, and once I specify the direction, that should uniquely determine the line. And so what we're basically doing is we're saying we just determine how much we flow along that direction. So sometimes instead of writing, x, y, z equals, p naught plus tv, we write x of t, y of t, z of t equals p naught plus tv. To just say that x is really, we're viewing it as a function of time. And once you give me one time, I then can figure out the x coordinate, the y coordinate, and the z coordinate. So this is how you do equations of lines. And so if I give you something in several variables, 3 variables, 4 variables, 5 variables, we need an initial point, and we need what we'll call the slope vector. And again, our general rule of thumb is we always want to try to reduce things to things we've already seen. And so I'll just end with just one other thing on a slightly different topic, on the definition of derivatives. So from calculus, what would f prime of x or df dx be? Remember the limit definition? It's the limit as h goes to 0.
Is it like f of x minus a h?
So f of x
minus f prime.
Let's think. We're trying to calculate the derivative. Here's x. What's the next point? It's a point.
x1.
We have a limit as h goes to 0. What's this next point?
Yeah. What do you mean?
We need 2 points when we're going to try to calculate. We're going to try to look at the average rate of change,
Yeah.
and then take the limit, and the average rate of change becomes
Y.
instantaneous. Well, what's the second point? The first point is x. And we're taking the limit as h goes to 0. The second point is x.
X plus h.
X plus h. We're seeing how much we've moved, right?
Yeah.
And so let's say, here's my function.
Oh, wait, isn't it like f of x plus h minus h f prime of h?
F of x plus h minus what?
F prime of h.
F prime?
No, f of h.
F of what?
X.
F of x divided by
H.
Because if you look at this, here is h. That's how much my x has changed. Here is f of x plus h minus f of x. That's the change in height. And so if you think of f as distance, this is how far you've gone, and h is how much time has elapsed. So this is the average speed from x to h. And then as h goes to 0, converges to what? So the average speed of a small and small interval converges to what?
The instantaneous
speed. So, we calculated a lot of derivatives last year, right?
Yeah.
So if I give you, table f of x, f prime of x, which is df dx. So if I give you x to the n, what's the derivative?
Nx to the n minus 1.
And if I give you cosine of x, minus sine of x. If I give you sine of x,
Cosine.
it's cosine of x. Give you e to the x.
E to the x.
And do you remember natural log of x?
1 over x.
Very good. So these are all the key derivatives. What if I give you some constant? What is it? It's 0. And so now we're going to just introduce some notation. We talked a little bit about this, partial derivatives. We saw this when we did the method of least squares. So df dx, this means partial, means hold all variables fixed but x, and then take derivative with respect to x. So this is called the partial derivative with respect to x. We sometimes write f subscript x to mean derivative with respect to x. So for example, if f of x, y, z is x squared y plus 3y cubed cosine z, what would the derivative of f with respect to x be? So keep all variables fixed but
2y.
Well, I would say 2xy.
Right, 2xy.
What's the derivative of the second
0.
piece? 0. What about df dy?
Then it would be x squared 9y squared
Plus 9y squared
cosine z.
cosine z. And so that's how you take a partial derivative. You just consider all the other variables the same. You're just as fixed and constant.
I think we did that last year. I think you showed us.
I think I showed it this year. I'm just quickly reviewing this. So later we'll see what does it mean for a function to be differentiable of several variables. We haven't done that yet. We've just introduced some notation. I didn't want to do too much tonight, but this is a good place to start. All right. Let me hit shut down.